All right, in this video, I'm going to cover the chapter 1, machine learning. Um, but specifically, I'm going to go over the linear regression. Okay, so yeah, so I just upload the chapter 1 the lecture note in the Blackboard. So please read the lecture note carefully. So the machine learning just they classified as 4 category. Okay, so supervised machine learning. Let's see here. Let's see. Yeah, so here type of machine learning system. Okay, supervised machine learning, and then unsupervised, and then there reinforcement learning. Okay, and then online the and batch learning. Okay, so but the other one is we can organize the machine learning as, let's see, yeah, instance based learning or model based learning. Okay, but the very I mean the base well, I'm going to go over the basic example of the supervised machine learning is a linear regression. That's also belong to model based learning. Okay, so let's see. Let's see. First one, we need to understand the mathematical background of the linear regression. Okay, so I'm gonna go over that one, and then if I have time, then I'm gonna go over the how to write the code. I mean, implement the linear regression using Python. Okay, so give me a second. All right, so yeah, I'm going to upload this lecture note in the Blackboard too. Okay. So supervised learning. Okay, so first one we need to I'm going to introduce some notations we're going to use very often. So starting from the question, how can we learn to predict the prices of other houses in Portland as a function of the size of their living area? So so first we are going to create the model or kind of mapping or function, okay, predicting the prices of the house. Okay, but not just in this case example, we're gonna see Portland, but in the homework you will see Boston. Okay, but anyway, so function of the size of their living area. So um, the first one, x, see that x of I, so that's the input variable or feature. Okay, so xi going to be what the actual living area, right? So we're gonna when we collect the data of housing information in Portland, okay, so we're gonna extract the living area. That's gonna be input variable, right? So now then let's see, y sub I, that's gonna be output. So here the output gonna be what actually the price of a house, right? Okay, so then or in you can say target variable that we are trying to predict. Key values x sub upper I and y sub upper I. But now what? The in general, so the actually the price of house will not be determined by only size of the living area, right? There are a lot of parameters we have to consider, not just size of living area, I mean, or let's say what size, the size of the house, and then the school district, and then neighborhood, right? Okay, and then what material the houses use to construct the house, to build house. There are a whole bunch of the parameters, right? So the let's see, now we'll see, give me a second. So the feature is not, in general, feature is not just one. Okay, so there are a lot of, of features we have to think about this. Anyway, so now x upper I, y upper I, that's going to be training example. It's called training example. Okay, so now and the x upper I, y sub I goes 1 through m. That means that we see that training set, the data set that we will be using to learn. So we're gonna use that training set. This is given, okay? When you collected the housing information in Portland, then we're gonna using the EDA exploratory, data analysis. We're gonna extract that training set. Okay. So I is the index of row. So the what the X upper I, Y upper I. This is kind of the train set in, I mean, X upper one, Y upper one. Okay, sub one, super one, and Y super one is just the first row in a training set. You can say that. Okay, so now the chi is the space of input value. Okay, I mean, script X, script X the space of input value, script Y is the space of output value. So now, okay, so a data set giving the living areas are prices of 47 houses from Portland, Oregon. See, so X sub 1, X sub 2. So you see that upper script, superscript, I mean, superscript represent the what? The index of example. Keep in mind this index of example. So X sub 2, 16,000 square feet, and the price is the unit of the price is $1,000. Okay, so 330. That's going to be value of y2 second. I mean the second target of the second example. Okay, and third example, the living area 24,000, to 2,400, and then the price target value is 369. Okay, so now next one. So here given a training set, our goal is to learn a function. We create a function, okay, from the input variable to the value to output values. So then such that h of x, definitely h of x must be a good predictor for corresponding value y. Okay, what does that mean, good predictor? It means that h of x is not only what not only just return those prices y sub 1 to y sub when we input x upper 1 through the x upper m, but also h of x must return good prediction of the prices when we input a certain living area, which is not in the example set, training set. Okay, keep in mind this. So all right, so now then h is called hypothesis. Okay, so this is the name of function. Okay, h is called hypothesis. So here training set is x sub look at this. Now we think about the general case. Okay, so see, so the superscript one, parenthesis number, that's the what index of the what I can say the example, right? Index of example, keep in mind this. Okay, and then subscript one, subscript, is the index of feature. Okay, maybe x super one, I mean x sub one, the super one means the means feature, the size of living area, and then x sub two, and then the super one means maybe the size of house. Okay, and then see the subscript represent the index of feature. Keep in mind this. Do not be confused. Now, using the training set, we're gonna design and implement the the algorithm. Okay, using the Python. So that's the actually what we have to figure out, right? Okay. So how can we design? I mean, the construct the what the h of x, I mean the function hypothesis, which return good prediction for the what input, I mean example, which is not in belong to training set. That's really we need to figure out. Anyway, so and then once we figure out h of x, okay, so we predict y hypothesis. Okay, so we call the learning problem a regression problem if y is in the real number. Okay, The classification problems if y is a finite discrete set. Okay, so so I'm gonna talk about classification problem later. But this classification problem has only returned the finite discrete. I mean, normally it's just integer. Okay, 0 or 1 or 2. Okay, does not return. Hypothesis does not return the real number. Okay, so uh, the example is please look at the yeah, for the example classification, please look at the lecture note, um, the chapter 1 lecture note. Okay, so now next one. Okay, linear regression. So to make our housing example more interesting, let's consider a slightly richer data set. It means that I told you, so we're gonna consider the more features, not only living area, but number of bedroom, number of bathroom. See, so I told you subscript in the info variable subscript represent the index of feature, okay, or we can say index of column, okay, and the superscript I inside parenthesis represent what, the index of row, where you can say index of example. Okay, so to perform the supervised learning, we must decide how we are going to represent hypothesis H in a computer, right? So keep in mind, hypothesis is nothing but function. Okay, so we wanna, yeah. So okay, so approximate y as a linear function. Yeah. So excuse me. So all right. So now we approximate the y, which is a target variable, right? Y as a linear function of x. So we're gonna we construct the hypothesis h as a linear function. See, theta 0 plus theta 1 x1 plus theta 2 x2. Give me a second. So here we only consider, what, in this case, we only consider, we assume that we're going to consider two features. Okay, x1, x2 means the x1 is a feature 1, x2 is a feature 2. Okay, so we only consider two features. So in an example, input uh, the first example, there is two features. For example, living x1 represent living area, x2 represent number of bedroom. Okay, and then what we're gonna do, we need to determine theta 0, theta 1, theta 2. Okay, so that optimal theta 0, theta 1, theta 2, that makes the hypothesis h to return best the what the good predict. This good predict. Okay, so here theta is called parameters, also called the weight. So parameterizing the space of linear function mapping from x to y. Okay, so x is what input value to y is output value, right? So in this example, y is a price of house, x is what the the set of what in the living area and the number of bedroom. Okay, so dropping theta in age of theta. Okay, so here age of theta. So yeah, so now I'll just drop the subscript theta. Okay, okay, and then we can by the way, so we letting x0 equals 1. Okay, then we have in this h of x is can be expressed like this. Now here we're gonna generalize the linear function h, okay, having the not just the two feature but n features. Okay, so and you see the n is a number of feature, or you can say number of column, right? So how many example we to consider? How many example? M. Keep in mind this. So superscript I goes 1 through m. That's a number of row, and the subscript 1, 2, 3, which is a feature index of feature, goes 1 through n. Okay, so then see a sigma theta sub j x sub j equals 0 through n. Then we can express that the expression as a vector expression. Okay, theta this is transpose of theta times x. Theta is a column vector. Okay, so theta is a column vector representing all the parameters, theta 0 through theta n. X represent what? Input variable. Okay, x sub 0 to xn. Actually, x 0 to x sub n represent what? Features, right? Okay, but we actually what? X0, we see that here in the example, right? I mean, in the linear functions. Give me a second. Mm. So in the here, there is no x0, right? But we just made up x0 as 1, okay? So we say theta 0 is nothing but theta 0 times x0 and the x0 1, okay? To match the size of the vector, okay? So x0 actually 1, okay? This is 1. All right, x1 is the what? The it represent what? The first feature, okay? So living area. X2 sub 2 represent what? Second feature, which is a number of bedroom. Through the xn is n feature, represent n feature, nth feature. Okay. So now here n is a number of input variable. Yeah, I told you. Okay, not counting x0. Okay. So now then h of x, see that here? This one, the x upper one, x super one, that is a column vector, okay? Keep in mind, this is a column vector. That is actually x upper one is what? X upper, that is x upper one means x upper one is, wait a second, x upper one, okay? That is a column vector. So x one, upper one, through the what? X, okay, upper one, and sub n, okay? So this input variable, x upper one, f super one has n features, okay, n features. So, okay, so you need to familiar with this information, the notations, okay? Otherwise, you're gonna get confused a lot. Okay, so now next one. So, okay, how do we pick or learn the parameter theta? So, defining optimal the parameter theta is called the learning. It's called the learning the parameter. Okay, learning the hypothesis or learning the parameter theta. So here we make h of x choose to y and list for the training examples. It makes sense. Okay, so first the first step, we have to determine parameter theta so the h of x will return a value which is close to y when you input the examples. Okay, so so to do that, okay, to find the the parameter theta which makes the h of x close to y, then we have to define the cost functions. So here's a cost function right there, j of theta. Okay, so now this is from the actually yeah, this is from the actual statistics. So j of theta is 1/2 of sigma h of x upper I minus y upper I squared. So see that this is what? That's the difference between the what? The h of x upper I super I, that's the approximation of the target value. Y super I is an actual value of exact value or the true value of target value, right? Okay, exact value of price, we can say that, okay? Taking square, okay, and then sum of them divided by 2. So it means that j of theta measures how close the h of x super i's are to the corresponding y super I target value for each theta. Okay, so So what does that mean here? This one, j of theta. Okay, so let's just, okay, just, dig out j of theta more, okay? So we're gonna expand j of theta. So it's a half of, 1/2 times the sigma, see, I equals 1 to m. Then I equals 1. I told you x upper, super I. See that? X super I. This is the column vector, okay? Y super I is a column vector. Keep in mind this. So we're gonna figure out, this perfect square for each I. Then when I equals 1, then we got this. And then h of x of I is what? Actually, it's the sigma of what? Theta j times xj1. You see? So give me a second. See sigma theta j xj over 1. That's the actual h of x super 1. Okay. This is h of x super 1 and then y super 1, right? Okay. And then when I equals 2, we're gonna get this. So sigma theta j times x sub j super 2, that's the h of x super 2, x super 2, okay? Minus y sub 2, okay? All right. So now, okay. So now is equal to, so to understand, the j of theta better, let's say m equals 3. What's m? M is the number of examples, okay? And then n is 1, that's the number of feature, okay? So the, keep in mind this. So then, till now, then what? X, let's say, theta 0. Look at this. So this is the straight line is the, what? The graph of h of theta, okay? And then horizontal axis represent feature and the vertical axis represent target. Okay, since we consider only one feature, right? Okay, so then we can plot the h of theta in a two-dimensional space, right? Feature and target. So x sub 1 upper 1, x sub 1 upper 2, x sub 1 upper 3. So these are represent what? The examples, 3 examples. Okay, it's 3 examples. It means that x sub 1 super 1 is, just the living area of the first house. This is x sub 1, x sub 2 is the living area of the second house. Okay, and then x sub 1, x sub 1 super 3, this is the living area of the third house. Okay, right. So you see that here. Okay, for each, the example x sub 1 super 1, x sub 1 super 2, x sub 1 super 3, for each example, then we can approximate the target value, I mean price of the house, right? Right there. That's the one. This is the point. The y value of this point, second variable or second coordinate of this point represent approximation of the price obtained by what? The hypothesis h of theta, right? Then, and then the, let's say actual the price of the house is, let's say y sub 1, y super 1 right here. Okay. Then there is a difference, right? Okay, the difference, that's this. You see that? Okay, all right. So, do you understand that, right? So the h of the what? The second coordinate of this that point is obtained by the evaluation of the h of theta. Is it okay? Actually, h of what? sorry, it's not h of data, h of the x, right? It's a typo, right? This is h of x. H of x is typo, I'm sorry. So now then, the sigma theta sub j x sub j super 1, that's the what? This is the what? That is h of what? H of x uh, super 1, right? Okay, okay. But I know in this example, j goes 0 through just 1, right? Okay, j goes 0 through 1, but okay. Now, then, so now we see that here, actually sigma theta j times xj minus y, that represent the distance between the what? The point on the graph of the hypothesis h, and then the point whose the second coordinate is the actual value, actual the target value. Okay, see. So we're gonna take a square of this distance for each example. Okay, for each example, take a square and then take a sum and then divide by half, divide by 2. That's the meaning of. Second, see, that's the meaning of this j of theta. Okay, so now you need to fully understand the meaning of cost function. This is really important. Okay, now then, least mean square algorithm. So the give me a second. Okay, so now then, back here, the cost function right here. All right, I mean, so right, so here goal is to find out. Goal is to make the hypothesis h close to y, right? So our goal is to find the optimal parameter theta to make the making the h close to y. So first we define the cost function. So how can you find out such a optimal parameter theta using that cost function? So that's the key, right? That's what we have to do. So then we're gonna use least mean square algorithm. Okay, just listen carefully. That's the key algorithm, the linear regression. Okay, so we're not gonna yeah, in Python we're gonna use just a package already made. This algorithm already made, okay, in the built-in the package. So you don't have to implement this algorithm, but you need to understand this. So okay, we want to choose data so that to minimize your data, right? But how? So use a search algorithm that start with some initial guess for data and then repeatedly change data to make j of data smaller until we converge to a value of data that minimize j of data. Okay, so start here, starting from the initial guess for data, and then we're gonna repeatedly change data, okay, to make j of data smaller, smaller, and then eventually what the j of data converts to the minimum value of j data, right? So then, so that's the strategy. Okay, so now then we're gonna use consider the gradient descent algorithm. That's the from the numerical analysis. So because that one is beyond of the this subject, I'm not going to cover in detail. But here's give me a second. Give me a second. Here's the idea. Okay, so now think about the geo data has a parabola like this. Okay, so we know the at which point geo data has minimum value right there. Let's see. right here. At this point, let's say data 0 hat. Okay. Then what are you gonna do? We're gonna find out what the derivative of the j equals 0. Actually, it's critical value, right? Data 0 has critical value, right? Okay. So we need to find out the derivative of j, derivative j with respect to theta. But here I know theta is not just a single number. Theta is what, column vector, right? Theta 0, theta 1, theta 2. Okay, depending on the number of feature, right? So we'll find out actually partial derivative j with respect to theta I. Let me say theta I equals 0. Okay, so we must find the critical value for each partial derivative with respect to theta I for each I. Okay, so that's the strategy. So now then, you see that here? Yeah, we're gonna do here. So now you see, this is the partial derivative with respect to theta j. This is partial derivative with respect to theta 1. So here we only consider the one feature. Okay, one feature. So then the derivative of the let's see, then partial derivative j with respect to theta j gonna be like this, and then partial derivative of j with respect to theta 1 is like this, setting that equals 0, setting that equals 0. Okay. So now then, yeah. So give me a second. All right. So now then, here's a problem. But oh, excuse me. Okay. So yeah. So here, yeah. So it's we cannot find out the what you see here, because you can see that here here theta 0 theta, we don't know theta 0 theta 1, right? We cannot solve that equation for theta 0 theta 1. We cannot solve the equation for theta 0 theta 1 because you see it is one equation. You see that right here, and then we don't know actually theta 0 hat, theta 1 hat critical values. Okay, so the I know so the what so since we don't know the actual critical value, I mean this equals 0 at theta 0 hat and theta 1 hat, but since we don't know theta 0 hat, theta 1 hat, that's a problem, right? So we don't know theta 0 hat, theta 1 hat. Okay, so now then what? The instead of finding since we don't know theta 0 hat, theta 1 hat, which are critical values, right? So what are you gonna do? Here, we're gonna find the what let's see, we're gonna find the let's say maybe just initial guess is right there. Okay, let's say this is theta 0. Here's the theta 0. I mean initial guess right there. So we find out the derivative of the I mean slope. We're going to find derivative of this tangent line at the initial guess here, and then we subtract what, since then we find out the tangent slope tangent value. Since see that the slope tangent value is a negative, right? That means the if you subtract what the value of j at this point, okay, subtract the value of j theta at this point, okay, then so that we got this, for example, we here, okay, we subtract the value of j theta from the j of theta at this point, not but I mean just the partial of the value of j theta, okay, then we know that the j of theta approach here, this point, close to the critical value, minimum value. Okay. All right. So that's the strategy. So we're gonna here go there, and we go there this way, and then we go that way, and then for each iteration, finally we approach the minimum value. So actually, that's the gradient descent method. So here. So this the algorithm of gradient descent method is this: theta j new equals theta j old minus alpha posture. See, theta j new equals theta j old minus alpha is the ratio. Okay, so alpha times partial derivative of j theta with respect to theta j. Okay, yeah, alpha is called the learning rate. So now then, yeah, so how can you find the optimal alpha? Yeah, that's other story. Okay, so this is behind this subject, so I'm not going to cover it. Okay, but so we're going to find out this. We already find out, right? So let's see. So we already found the partial derivative j with respect to theta j, theta 1 right here, right? By the way, where that comes from? Yeah, I didn't cover it, but yeah, you can see this one, but let's see. Let's say for example, let's see. Let's see. Okay, so we consider the m equals 1, which is number of training example, n equals 1, which is number of feature. Then j of theta gonna be half of the what h of x super 1 minus y super 1 square, right? Yeah, but h of x super 1 is what? Actually theta 0 times x super 1 sub 0, which is 1, right? So theta 0 plus theta 1 x1 x sub 1 super 1, right? Excuse me. Yeah, so now then yeah, see, so we got this theta 0 plus theta 1 x sub 1 super 1 minus y super 1. So yeah, so let me drop the superscript parenthesis 1. Okay, so then now see theta 0 theta 1, that's unknown parameters, and the x1 and y is the input, I mean training example, right? Okay, so now the gradient, this is the quadratic equation, right, of theta 0 and the quadratic equation of theta 1. That's what we got the that parabola like this. Okay, and then it's not a big deal to find the partial derivative of j with respect to theta 0 theta 1, right? Okay, so now we got this. Now we're gonna plug in this one into what? Into the gradient descent algorithm. Okay, then for the data, then we can update theta 0 and the theta 1 respectively. Okay, so now let's see, in general, with a single training example. Okay, so a single training example, the partial derivative j with respect to theta j gonna be the half of the partial derivative of half of the h of x minus y square, because we only consider one single training example. Okay, all right, then that's gonna be the what 2 times or half times h of x minus y times partial derivative of h of x minus y with respect to theta j. Okay, all right, so now, but here keep in mind is, in this case, from here we consider the what n what n what, give me a second, n features. Keep in mind this. Okay, so we in what up to here we consider the just one feature, right? But from here we consider the n features. Okay, so considering n feature, then the h of x gonna be sigma of what x theta I xi I goes 0 through n. Okay, the partial derivative of this guy gonna be what? Think about this. Partial derivative of this one with respect to theta j gonna be what? X sub j, right? X sub j. All other terms gonna be gone, because all the other terms will be considered as what? Constant. So partial derivative of that one with respect to theta 0 is what? 0. except for theta j times xj. Okay, so now we got this. So now you see that actually the general form of partial derivative of j with respect to theta j is going to be this. You see? Now then, so now we see that. Now then, for the cost function, the gradient descent method algorithm going to be rewritten as like this. You see that y minus h of x. You can see that here there was a negative sign, right? But if you put the negative sign inside the parenthesis, that's why h and y are going to be swapped. So now the y minus h times xj, where that comes from? Now you understood it, right? This is actually partial derivative of j with respect, cost function with respect to theta j. Okay, that is called the least mean square. Okay, method. Least mean square. Okay, update, or also known the with the half learning rule. Okay, so see now the using the gradient descent algorithm, we can find the optimal theta. Okay, and then applying the plug-in, that data, optimal data obtained by the gradient descent algorithm into the hypothesis. Okay, so now yeah, so I'm not, yeah, so the if you are interested in the mathematical background of this linear regression more than just read the rest of the lecture note. Okay, but so that's the main algorithm, main mathematical background of the linear regression. Okay, so right there, give me a second. So where's one? Yeah, so here, so training set, we're gonna get training set from the in real world. Okay, in real world, we collect the data and then using EDA, exploratory data analysis, we're gonna extract the we're gonna clean the data. First, in the real world, we're gonna get raw data. Okay, we need to clean the data. Okay, reshape and clean. Okay, in the data first. Once we clean the data through the EDA, so we use the data as training, but not just all of them. We need to, yeah. Anyway, so we're gonna get, once we get the training set, then using the learning algorithm, especially in linear regression, we're gonna use gradient descent algorithm. Okay, gradient descent algorithm. The actually at least mean square. Okay, so we find the ultimate theta. Okay, in the hypothesis. Once we get hypothesis, and then we train the hypothesis. Okay, so now the to so now we can use the h to predict the what y. Okay. So the give me a second. So let's see. Yeah, let's move to the, give me a second. Let's move to the Python, okay? Linear regression practice. All right, so here, this is the machine learning linear regression practice Python code, okay? So, we're gonna talk, so here, we assume that, yeah, so want to predict the housing price for a region in the USA, okay? So the data contain the given, the data has the following columns. Okay, average area income, average area house age, and then number of rooms, number of bedroom, population, price, address. Okay, so what we need, the library, what we need is pandas, definitely, numpy, and then matplotlib, repyplot, then c1. Okay, so to make the graph too fancy, we comment this. Okay, so now yeah, how USC housing, the CSV file we import. Okay, so and then yeah, so see, this is the data right here, average area incomes, and then age and rooms and the bedrooms and then population. But let's see, the average area number of bedroom, it should be at 4.09, 3.09, yeah, but And that's okay, but normally it should be what? Integer, right? 435. Okay. So how many bedroom here in the house is 5.13? That doesn't make sense, right? It's normally integer, right? So yeah, you can change the round this features, okay, the value to get the integer number. And there's a price. You see that 1.0590, for the first example, in the price that feature, the value is 1.059034 and 10 to the 6th power. And this is actually 1 million, right? 1 million, let's see, give me a second. It should be 1,059,034, isn't it? Let's see. Okay, so the I think a unit of this price going to be billion or point million, right? Point one point million. So it's huge. Okay. So anyway, so and then information of the data that data frame US housing. So all of the features or data type is a float 64. Real number except for last one address, the object. The category, right? That makes sense. Okay, so now US housing describe. From here, this comment we can figure out the what basic inference statistic of each features. So now let's see average area income. The mean is let's see what 6,008 what 68,500 let me see 68,583. Okay, that's the mean. And then let's see price is mean is yeah, so 1.232073 times 10 to the 6th power. Okay. All right. So now we'll see. But by the way, look at this, because we want to predict the price of housing, right? That means the price that feature must be what? The target variable, target feature. Keep in mind this. So average area income through the area population. These are the what features. Okay, examples. The features of in the example. Okay, price gonna be what target value. So we have to take that out. Okay, when you input in the hypothesis. So, but before doing that, let me do EDA. So let's figure out correlation between the price and then other features. Okay. So now, then one thing that see right there, you see here, this one, the average area income and the price. As average area income is increase, price is increase. You can see this, not um, exactly correlated between the average area income price, but you can see that, right, a little bit. Okay, you see that there is a correlation relationship. Okay, but then you see this DIST plot. This give us the what give us the distribution of the data price. Okay, so but see that you can see that here the data is what price data. The price is normally distributed. You can see that. Okay, let's see. So by the way, yeah, okay. So the original axis represent price, right? And then the vertical axis represent the probability, right? Okay. Now, give me a second. Let's see here. Now look at this. How is possible? We got. We got the normal distribution for the price. Yeah, but we'll see it later. But actually, this data is a made up data. Okay, so but we'll see. And now, also we can figure out the correlation by graphing this one heat map. Okay, now this is the average area income versus price. a little bit the red. So it's between, I think around the 0.6, or that you can see that 0.6. That means what? This is the value of the correlation. Okay, so it means the average area's income is correlate with the price. Okay, what about the black? Black means the correlation is 0. There is no relationship between two the features. Okay, so keep in mind this. And then see that here, the diagonal. You see that in all the diagonal block, the color is what? The skin color is kind of one, right? The value is one, right? It makes sense because the correlation between the average area income and average area income must be what? One, right? Now, now we're gonna create a linear model plot. Okay, so using a C1's LM. LM is a linear model. Okay, okay. So using this code, we gonna, so once you figure out that there is average area income and the price, there is a correlations, not fully but partially. So now we just plot it. Okay, so now here we're gonna start from the the construct the linear regression model. Okay, so first one, to training a linear regression model, what does that mean? So the for each example, I mean through the example, we're gonna find the optimal, through the example, we're gonna find the optimal theta. I told you, right, in the hypothesis. So first of all, we have to divide feature, I mean examples and example and features and target. Okay, so we know that X must be, well, all of the features in the data frame except for the price, right? The Y must be target column, right? Target value. So now, train test split, what does that mean? So think about this. Given data, USA housing, once we construct the model hypothesis, we have to uh, test that model hypothesis if this is really return good predictor, good acceptable or good predictor, right? So to test the hypothesis after training that hypothesis, we have to divide the given data, given data USA housing as training data and then training data and test data. Okay, so how can I do that? Normally we do excuse me, 6 to 4 or 8 to 2, the ratio. Okay, the 80% training, 20% of data is used as testing. Okay, so but we don't just we're gonna divide the data randomly. Okay, we're gonna randomly choose the training data 80% of 80% of the 80% of the USA housing as a training data randomly. Okay, so we also randomly choose the testing data. Okay, we're gonna do this one automatically using that command. Okay, so from sklearn dot model selection, import train test split. So x train and then test, and y train, y test, and the train a test split x y. So you see, what is x? X is what? X is all in the data frame USA housing, all of the feature except for price. Okay, and the y is a price column, right? And the random state, the test size is 0.4. It means that what? That we're gonna divide the test data into 6 to 4. Okay, and then random state 101. Yeah, so I'm not gonna talk about this one. So just search this one, all right? About this one by yourself. And then creating and training the model. Okay, so now we're gonna, okay, linear regression, I mean hypothesis. Now we're gonna define optimal theta, okay, using the least mean square. All right, so for the what, give me a second. Yes. So now then from the sklearn.linear model, the import the linear regression, LM equals linear regression. Okay, so LM is actually hypothesis. Now we're gonna input X train, Y train into the LM, that model hypothesis. Okay, so we trained that, we done. It's really simple, right? Just three command. It's really simple, but you see the mathematical background, these three command is really huge. We saw that in lecture note, right? So the model evaluation, now we have to check that whether or not this model hypothesis really return really good predictor. Okay, so first one, LM the intercept, yeah, this one give us return print out the uh, intersection of the linear model. Okay, this is this, and the coefficient df, that one return the what, theta 0 through the what, actual theta 1 through the theta what, n. Okay, data parameters, coefficient df and PD data frame lm. You see the lm dot coef and then underscore. That will give us the what, this is the what that one has the parameter data. Okay, so we construct the data frame using the lm.coef and then column in a x, the feature. Okay, and then but see we we have column label, right, for that parameter. So we add one more, I mean, so x dot column, that it means that we're going to use this one as the index, lm.coef underscore, that we're going to be well, the attribute. Okay, and then column equals coefficient, that will be set what coefficient as the what column label. Okay, so now here, let's see, what does that mean? So holding all other, interpret the coefficient, holding all other features fixed, 1 unit increase average area of income is associated with an increase of $21.52. Okay, so you can see that right there, but does this make sense? That doesn't make sense. Probably not, because I made up this data. Yeah, I told you. Okay, so here's the homework. Actually, if you want the real data to repeat this sort of analysis, check out the Boston data set. I posted the homework to for the linear regression using the Boston data set. Okay, so that's what you have to do. And then prediction from our model. Once you train the model, then using the X testing data, we're gonna check that if that model is really good or not. Okay, so the predictions equal lm dot predict x test. What does x test? We just plug in x test features, test data into the model hypothesis. The prediction gonna be what, expect the prediction of the y, prediction target value for that x test. Okay, but we know actual true what price for the x test, which is y test, right? So we can compare y test and prediction. Prediction kind of approximation. Okay, approximation of y test, and the y test is true value, you can say that. So now we see that we're gonna get the almost correlated, right? Let's see, 0.5 and 0.5. You see that is almost the linear, right? Y equals x. Okay, see that. But this is not numerical analysis. Okay, our goal is not to the exactly. I mean, we're not gonna try to approximate with highly accuracy. No. Okay, keep in mind this. This is different from the numerical analysis. Keep in mind this. So the machine learning, the goal is to how can we create the model generally what predict, okay, I mean, how just we're gonna goal is to create the model that predict not just accurately one specific input, but generally, return good price, good target value. Okay. So now, then also we're gonna plot the distribution of the differences. It's normal distribution. It means really good. See that most of the differences value is along around what zero. It means that most of the predictions in the y-test, their values are almost zero. Most of the data, most of the examples. Okay, this is really good. And then, but when you look at this, let me see. And then how can you measure the residue? I mean, different. How can you measure the error of the prediction? We use three. Normally, we use three metrics: mean absolute error, mean square error, root mean square error, RMSE. RMSE is the most popular, okay, the measurement tool, okay, tool to measure the error, okay. This is square root of 1 over n, okay, and then y. So what is I? I told you I is what? I mean, n is what? A is a number of example. Keep in mind this. So here, yeah, so I'm sorry, this is it should be m, okay, yeah. This is different from the the lecture note, right? My lecture note is different from my lecture note. It should be m, not n, but okay. So now, I mean, I'm sorry, it's confused. Here, I'm sorry, not m. Sorry, this n is actually the what? The number of example in X test. Sorry. Okay. Now, we how can you measure this in the Python? We're gonna call the import the metrics in sklearn. The sklearn is the library of the package, collect all the packages about the machine learning. Okay, so give me a second. So you see the metric that mean square error that will the command of mean square error. Okay, and then look at this. RMSE is the square root of the mean MSE, right? So we do mp dot square root is command in NumPy, okay, and then metric dot mean square error that will return the what mean MSE, right? So mp dot square of the metric dot mean square error that will turn the square root of the what MSE. You see the problem? Look at the number RMSE. This looks quite big, right? You may expect that okay, RMSE is going to be maybe 10 to negative 3. No, I told you this is not the numerical analysis. Okay, don't think like this one in numerical analysis. This one, so it still looks big, but actually this number is less than what? Give me a second. Less than variance of the standard deviation of price. You see that? Standard deviation price target value is 3.531176 to the 10 to the fifth power. So this is the actually what? This is a 1.02278 times 10 to the fifth power, is it? Okay. So the RMSE is I mean, not 10 to the fifth power. I think we see 1, 2, 3, 4, 5. Yeah, 1 point. So this is less than standard deviation of price. Okay. So, but actually, think about this. Actual, I mean, price of houses is normally million, right? So, but RMSE is just, I think, just 102,278. So it's not that big. Okay. So now that's all about the linear regression practice. Okay, so please you need to fully understand the mathematical background of the lecture. Okay, so linear regression, and then also you need to understand this code. Now you are ready to work the homework and then project. Okay, so let me stop here. Okay, so now then any questions, just send the email. Okay. So now next week, I'll cover the classification, okay, model. All right, that's for today.